Our next talk is a fully verified persistency library, and the talk will be given by Brijesh.
Great. Thank you. So I should speak into the microphone, is that right? Okay. Yeah, so this is a joint work with a number of people that you can see on the screen. Heike is also here in the audience, so maybe she'll be able to answer some questions that I'm not able to answer. But this is basically an exercise in verification, I would say, and we're trying to verify a particular library that allows you to transform a concurrent algorithm, a linearizable concurrent algorithm, into one that's called a durable linearizable concurrent algorithm. And the proof is via a number of smaller refinements, very small refinements, and a few sort of techniques to sort of transform the algorithm as well, which I'll talk to you about in a second. Okay, so, right, and persistency, right? So there's this sort of this mysterious word that might be a little bit confusing to some people. So what is persistency exactly? So the sort of architecture we're looking at is a bit like this. So we have multiple threads, concurrent threads, accessing two different types of memory. One is a volatile standard DRAM, but also this sort of non-volatile memory, which became very popular for a long time, well, for a while, because Intel invested a lot of money into this Optane technology, which they then pulled the plug and made a lot of people disappointed. But this is sort of this technology that allows you to sort of treat this non-volatile sort of persistent memory in a byte addressable way. So it's very efficient compared to sort of standard storage. And yeah, so various technologies, Intel, which is now discontinued, exists, but sort of others are sort of picking up the pieces. For example, CXL and memory semantic SSDs and so forth. So this research is still sort of ongoing, even though Optane has died, is what I'm saying. Essentially, what it allows you to do is sort of develop very high performance recoverable applications. Okay. So just in case you're not sure what happens with persistent memory, you kind of have two copies essentially of your data, and you first start writing to DRAM, and then occasionally that's sort of backed up to NVRAM. And the good thing with the NVRAM copy, even though it might be a little bit stale at times, is that if you ever have a crash, you can recover from it, right? So you can sort of copy back your non-volatile memory into DRAM, and then you've got sort of some kind of recoverability possibilities, which you didn't necessarily have if you just used DRAM. So you basically you don't have to start from scratch. Okay. Just to give you some idea of what you can do, you can sort of control the way you write to persistent memory. So programmers are expected to control the way you write to persistent memory, because otherwise you will end up with inconsistent algorithms and incorrect algorithms. And you can sort of use sort of various instructions that developers have provided, or hardware developers have provided, such as persistent writebacks, which is this PWB, and this pfence instruction. And just to sort of show you some example programs, these are 4 different examples. They're not sort of interleaved, multi-threaded examples. They're 4 different examples. They're all single-threaded. Just to sort of show you what goes on with persistent memory, I'll sort of talk through the 4 examples. And the way to sort of explain this easily, I think, is through this thing called a durable invariant. And the durable invariant is basically an invariant over the non-volatile memory. Okay. So what happens in this program here is, well, we're assuming all locations are initialized to 0. In this little program here, the writes can be persisted at any point in the execution. And so the only durable invariant you're sort of guaranteed is that either x is 0 or x or 1, and the same for y as well. Because one of the things that could happen is that the whole program could execute, and then both the x and y's have both persisted. Right. Now, if you insert these PWBs and pfences, you get sort of more guarantees. So the durable invariant you get for this little program here is that if y is 1, meaning if y has been persisted, then we're definitely sure that x has also been persisted as well. Okay, that's the idea. Now notice that the PWB has a very special function. It kind of works together with the pfence. So if you just have the PWB by itself, then you don't actually get any guarantees. So the point of the PWB is to sort of to tag locations that you want persisted when you see a fence. Okay, so if you just have the PWB in this program here, then you actually don't get many guarantees. You're kind of back to where you were before. Okay, but one thing you can do with PWBs is you can sort of efficiently tag many locations and then do a fence at the end. and then do a write. And here you can see that in this little program here, I've got two locations that I've tagged as PWB with PWB. And then I've done a pfence, and then I've done a write to Y. Now, what I'm sure about is that if I have Y equals 1 at the end in my persistent copy, then I'm sure that also X and Y have also been persisted as well. Okay, so that's the nice guarantee you get. Okay, and sort of the second part of the story is that we kind of want to talk about sort of concurrent objects. And by concurrent objects, we want to sort of talk about linearizable concurrent objects. And in case you haven't heard about what linearizability is, it's a condition that was developed over 30 years ago, 35, getting close to now, by Hurley-He-Wing. And basically, it sort of says that, provides a sort of concurrency guarantee that concurrent object sort of somehow takes effect instantaneously between its invocation and response. And you can sort of linearize these operations in a way that it's sort of consistent with the sequential order, with the sequential specification. That's the idea. So that's a very short tour of linearizability. I won't say any more about that. But essentially, there's been other conditions that have been developed, like durable linearizability, and that kind of extends this idea of linearizability to durable objects. So what does it mean for a persistent object to be correct? Well, it has to satisfy this one condition well, there's several conditions that have been developed, and one that's quite popular is this idea of durable linearizability. And so essentially what it says is, it's a very simple idea. You basically have histories with invocations, responses, and also crashes and you record all of that information in your history. And what you require is that if you take out all the crashes, then you get back a linearizable history. Okay, so an example would be something that looks like this. You've got three kind of threads executing a put and a get operation on some shared location. And it's basically just a store. Like you can think of the R as being some kind of store. So we've got to put R, again, I'm assuming that R is initially 0. So put R 1, thread 2, well, there's a crash, and then thread 2 gets something, and it happens to get 0, and then you notice that here you get R equals 1, right? And that looks a bit strange, but this is actually still durably linearizable, because what you can do is you can take out that crash. And what linearizability allows you to do is it allows you to sort of extend incomplete operations. And when you do this, you kind of end up with history that is actually linearizable, because you've got sort of three concurrent operations now, and you can linearize the get before the put, and then the put before the get, the second get, right? And that's actually linearizable. It looks a bit strange, but it's actually something that's allowed by durable linearizability. Okay. So that's the story of the background. And so what we're interested in is developing concurrent objects that are correct on non-volatile memory. And we want to, well, what are the options? One option is to sort of develop everything from scratch. You've got this new kind of hardware, and you develop the implementation from scratch and prove it to be correct. The other option is to sort of do something a bit more clever, which is to sort of take legacy code, legacy algorithms, and then sort of transform them to this new paradigm, if you like. Okay, and then what we're interested in is understanding whether this transformation is actually correct. Okay, that's basically the essence of the paper. And a lot of people have tried many different, proposed many different solutions for the second option, which is this transformation. And for durable linearizability, there are a number of proposals. There's another correctness condition called buffer durable linearizability, another proposal called montage. What we're interested in is this particular one, FliT, which was from, I think, last year or the year before. It provides a very simple way to transform concurrent linearizable objects into durably linearizable objects. Okay, so what it basically does is it provides a library, and it provides three operations, a library write, a read, and a complete operation. And what you're expected to do is you're supposed to take your linearizable object, replace all the reads and writes by libwrite and libread calls, and then before the operation completes, you call this complete thing to sort of do some final cleanups. That's essentially what you do. Okay, and yeah, so the library is super simple, right? So what you do is whenever you see a write, You start by calling some pfens. There's something called a FliT counter, which you increment using a fetch and increment, which is a read, modify, write. Then you perform the write itself. Then you perform a PWB. So this PWB is, oh, by the way, FliT stands for flush if tagged, right? And so what we're doing is we're trying to tag things using this PWB. So here we're tagging the write that we've just written. Then we do a pfence, and then we do another decrement of this FliT counter. Okay, I won't go through the details of this algorithm in detail. The interesting bit is in the read. What's happening in the read is that the read is sort of checking that there's no concurrent write that's being executed at the moment, and you can sort of work that out by looking at the FliT counter. So if the FliT counter's value is greater than 0, you know there's a concurrent write that's being executed. So what you then do is say, okay, well I better make sure that later on I'm going to flush this value. Okay, and the way you do it is you sort of tag that location as being something that I've read that potentially is being written concurrently by another thread. Okay, that's the idea. And finally, there's a complete operation. Like I said, it just does some cleanups, but the cleanups are super simple because you just do a pfence at the end, and it makes sure that everything that you have read that is potentially unpersisted does become persisted. Okay, that's the idea of FliT. Yeah, quite simple, I think. Okay. And the theorem that we want is, or the theorem that is also stated in the paper is this idea that you can sort of use FliT to transform algorithms from a linearizable algorithm into a durably linearizable algorithm. And what we mean there is we're replacing sort of the reads and writes in the object O with calls to the FliT library instead. Okay. And that's basically what we tried to prove. Well, what we did prove. Well, we started by trying to prove it, and then we actually proved it. And the other thing that sort of the other complication that comes up is the memory model itself is not as simple as just this writing to shared memory directly. You kind of use this TSO memory model, which is the memory model from Intel, which means that you have these store buffers that get in the way. I won't go into the details of these, but if you've seen any weak memory model talk, then you probably may be familiar with this kind of thing, right? There we kind of have to think about, well, what do the persistent writebacks mean, and what do the pfences mean, and so forth, and there are some proposals there. Okay, so when we do this sort of transformation to the actual hardware, we end up with code that looks a bit like this. Now we need to give some semantics for all these instructions, and well, we can do that because Ori and his then postdoc Artem wrote this nice paper about how you can sort of actually give a semantics and operational semantics for this for these persistent x86 instructions. And that's the semantics we use. Okay, so ultimately we end up with sort of a more complicated version of the theorem that looks a bit like this, where we're not only talking about FliT, but we're talking about FliT executing in px86. So it's actually, it's in a reflection of a real implementation. That's kind of what we end up with. Okay, well, how do we prove this? There's a number of steps. Like I said, the proof is literally breaking it up into smaller and smaller problems, and proving each of these smaller problems one little bit at a time. Okay, and so what we did first is came up with some kind of intermediate spec. So this jump from SC sequential consistency over to FliT with x86 is pretty complicated, even though FliT itself is quite simple. That jump is more complicated than one might expect. So essentially what we did was we came up with this intermediate library called PLib, which is a persistent library, and it basically sort of captures the essence, we would say, of FliT on px86. So that's step one. Step two is sort of to prove that if you can replace the SC, this is SC over here, which is sequential consistency memory model, by the PLib library. Okay, so this is an abstract library, and we can sort of do that replacement. And this replacement itself sort of guarantees that you end up with a durably linearizable object. Okay, that's the idea. And now we have PLib over here. Well, we can actually just, we know that refinement is monotonic, so we can actually replace the PLib gradually by FliT executing on x86. So that's the three main proof steps. And I'll sort of briefly talk through, I don't know if I've got much time.
Few minutes.
Few minutes, yeah. Okay, I'll briefly talk through some of the steps. Okay, So the PLib spec, you're probably better off reading the paper, because I'm just going to give you a brief idea of what it does. Like I said, it abstractly captures the essence of what FliT does. And the library sort of tracks, again, abstractly, every read sort of tracks the write that it read from. And then when you're doing writes, you have to sort of check certain things, for instance, that all previous writes have been persisted, and if you've got any sort of dependent writes, then those are also persisted, kind of thing. And then sort of, okay, well, there's a formal model, and you do some standard things like build models, essentially, right? And there's also this log, which is sort of used to sort of do this sort of tracking of reads, and each read and write has some flag that tells you whether or not something's persisted, and so forth. Okay, all right, details. And you end up with some automata that looks a bit like this. Details are in the paper, but when you're doing reads and writes, the library sort of double checks that in the log that you're doing the right thing. Okay, it's doing the thing that I just said in the previous slide. For instance, when you do a write, you're checking that all the persisted dependent writes from previous that you depend on are already in persistent memory, kind of thing. And only then can you perform a write. And so forth, right? And then there's sort of many details there that I'm just going to gloss over, kind of thing. But yeah, again, feel free to please read the paper. Okay, so once we have that, we have done this. Okay, so next we need to prove correctness of this theorem, but this time we're proving this transformation part, but with SC replaced by the PLib. And again, so we transform this into a refinement problem. We can use results from many years ago. Okay, I'm going to skip this completely. But you'll just have to believe me that ultimately we end up putting a tick there to say, yeah, that's been done. Okay. So that was step 2. And then the final bit is replacing this PLib by FliT executing on x86. Okay, it's the final refinement that you have to do. And again, it's split up into 2 further smaller proofs where we kind of developed another intermediate memory model called weak PSC, which is, I guess if you're not in this literature, then maybe you won't find it so interesting. But it's sort of SC strengthened with persistency, but again weakened slightly to cope with certain things that Intel x86 allows. So that's the idea. And now this was, I would say, a standard proof. It didn't involve any sort of transformation or anything like that, but still difficult. But the thing with this is that this has been mechanized and it's available as part of our artifact. And the proof was done by Gerhard Schellhorn and Stefan Bodenmüller at Augsburg. But yeah, that's there. Okay, so that's the final tick, and that gives us our final theorem. And there's the summary. So essentially, hopefully I've told you that libraries such as FliT, Mirror, and so forth give you some way of transforming linearizable objects into durably linearizable objects. And it's actually possible to prove it, but it involves some amount of effort and a big team. Thank you.
We have time for a few questions. Yes, Sankal.
Thank you. Very cool work. Very nice to hear that you've mechanized the proofs. How do you mechanize them? Can you talk a little bit more about the details?
Yes. So
interested to know how you model all the behaviors and what do you mechanize them?
Yeah, I mean ultimately all the models are represented using I/O automata, input-output automata. We could have used any theorem prover, really, but the theorem prover that's developed and that Gerhard uses, Gerhard Schellhorn, who is the main driver of the mechanization, is KIV. It's called KIV, Karlsruhe Interactive Verifier. And yeah, if you want details, you can check out our artifact, and you can say, yeah.
Is there an assumption on how O of SC was proven, i.e. if prophecy variables were used or not?
Yes. So there is a notion of a prophecy variable that we had to use. So it's well spotted, actually. So actually, let me just sort of double check that I understood your question correctly. Which bits were you talking about?
If you prove O of SC linearizable, are there restrictions on what techniques you can use to prove O of SC?
Well, no. O of SC is being linearizable is an assumption.
Okay, so there's no, like you can transfer whatever technique was used to prove O of
Yes. So O of SC being linearizable is an assumption. There is a prophecy variable that is used. I might use this sort of opportunity to sort of point this out. When we're considering these sort of traces, you have to be careful. Well, we want to do it in a forward manner, but you have to kind of know that the thing that you're reading from or writing from is going to be persisted at the end. Okay, so that you kind of do have to leverage information from the future and bring it to the past kind of thing. Yeah, but you can read out our paper for that.
Thank you.
Okay, so let's thank the speaker again.
Okay, thank you.